Now on to the second topic of numerical methods, namely numerical integration. And in this video I'll be giving a short introduction to that. So this chapter focuses on the common problem in mathematics to calculate the definite integral, which is defined in this way, where I is the integral from a to b of this function f of x dx. And graphically, the integral represents the area under this function f, bounded by the values a and b. And analytically, the integral can be solved using the antiderivative of f. However, you might find it necessary to use numerical integration when this function f is a very complicated function that is either very difficult or perhaps even impossible to calculate analytically. And alternatively, numerical integration might be necessary when you are not given this expression of the function f of x, but you only have a discrete values of f of x and f of x at a number of points. So you do not have a continuous function, but you have tabulated data, which is often the case with experiments or so. And yeah, here you need to use numerical integration. So the most common numerical integration methods are the Newton-Cotes formulas. And the Newton-Cotes formulas rely on replacing the function or the tabulated data with an interpolating polynomial that you can and is easy to integrate. So that's presented in this equation, where you approximate this function f of x that you want to integrate with a nth order polynomial fn of x. And recall from the interpolation videos that you can fit a polynomial of degree n through n plus 1 data points. So these figures, the Newton-Cotes formulas are depicted, a graphical interpretation of it. So you have this function f of x plotted in blue. In the first figure, figure A, you have two data points, and you construct this interpolating polynomial through the two data points, such as we did in the interpolation videos. And then you calculate, or you approximate the integral by calculating the area under this straight line, just the area of this trapezoid. And in figure B, you use three data points to construct a second order polynomial, and your integral is going to be the area under this parabola. So one way in which to make, to approximate the actual integral more closely is to not just apply a Newton-Cotes formula just once, but again to divide the whole interval into individual segments, and for each segment you'll approximate the function using a polynomial and calculate the area under this polynomial. And here this is done with straight lines.